Now we're going to take what we learned in the last lesson to cover how to convert between entire radicals and mixed radicals. So we know that if I take the square root of a number times the square root of another number, I can just multiply those two radicands and put it inside of one radical symbol. I can do the same thing if I am dividing, which means that, like what we did with the last practice in the last lesson, I could always take what those two numbers are and then split them up. So if I was to take 24 and divide that 24 by 4, it would be the same as 4 and 6, which means that I could rewrite the square root of 24 as the square root of 4 times the square root of 6. If I had the square root of 18 and I divided it by 9, it would be 9 and 2, which means I could say this would be the same as the square root of 9 times the square root of 2. If I did the same thing for a fraction where I had the square root of 11 over 4, then that's the same as the square root of 11 over the square root of 4. Now, if I am plugging these irrational values into my calculator, and I took the square root of 80, that's going to give me 8.94427. If I plug into my calculator 2 times the square root of 20, I get 8.94427. And conveniently enough, if I plug into my calculator 4 times the square root of 5, I get 8.94427. What do you notice about the answers? They're all the same. This is 3 different ways of representing the same radical. Now, why are these equivalent? Well, 80 is the same as 4 times 20, or the square root of 4 times the square root of 20, and the square root of 4 is just 2. So 2 times the square root of 20. If I divided 80 by 16, I get 16 and 5, or the square root of 16 and the square root of 5, and the square root of 16 is 4 times the square root of 5. If I had the square root of 80 where there is no coefficient, we call that an entire radical. If it has a coefficient like 2 root 20 or 4 root 5, we call that a mixed radical. So, entire radicals are always in the form of the root or the nth root over b. And mixed radicals will always, like I said, have some form of a coefficient, whether that coefficient is a fraction, positive, negative, whatever it happens to be. To determine if an entire radical with an index of 2 can be expressed as a mixed radical, we need to check if the number has a factor that is a perfect square. So, if I'm taking the square root of 108, there's 2 ways I can do this. I can either use my factoring tree, where I take 108, and I can split that into 2 and 54, 2 and 27, 3 and 9, and 3 and 3. And remember from previous lessons, if I have a prime factorization, it's a perfect square if there is 2 of the same prime number. So any set of 2 of the same prime number is a perfect square I can pull out. And if I'm removing a perfect square from a radical, then I'm going to take one of the set of 2 and move it out, one of the set of 3 and move it out, which is the same as taking the square root. Anything that does not have a pair has to stay inside of the radical, because you can't take the square root of something that doesn't have a pair. And 2 times 3 is going to give me 6 root 3. If you want to just say what is the biggest perfect square I can divide out of here, then mostly it's about memorizing what the perfect squares are, and that method works fine too. For 108, I can divide that by 4. I can divide it by 9, or I can divide it by 36. And in this case, 36 is the biggest perfect square I can divide out of here. So I would say that's the square root of 36 times 3. And the square root of 36 is the same as 6. So I can simplify this to 6 root 3. Either of these two methods work, and both of them are enough to show your work. Don't just jump to the final answer, but show me how did you split it up, or if you show me how you did a factoring tree, that's fine. So if I'm converting these two radicals in mixed radical in simplest form in this term means divide out the biggest possible perfect square. So for 50, there's only one perfect square that works. If I want to use a factoring tree method, it's going to be 2 and 25, and then 5 and 5. So I have a set of 2 5s, and one of those 5s is going to make it outside the radical, and the 2 that's by itself has to stay inside the radical, so that'd be 5 root 2. If you want to show it to me the other way, you could say that the square root of 50 is equal to the square root of 25 is the only perfect square I can divide out of there, and the square root of 2, and that's going to give me 5 root 2. Either of these methods is acceptable. If I'm doing B, then I could say that 45, the only perfect square I can divide out of there is 9. And I'm left with 5. So the square root of 9 times the square root of 5, and that's going to give me 3 root 5. Now here's where the factoring tree seems to work better, if we're dealing with bigger numbers. Once I get to 320, there are multiple perfect squares that I can divide out of here. There's not just one. So I might not always know what the absolute biggest perfect square I can divide out of here is. I know I can divide this by 4. And then I'm going to be left with 80, which would give me 2 root 80. But this can still be simplified, which means I didn't pull out the biggest one. 80 is still divisible by 4. And then I get 4 and 20. But then 20 is divisible by 4. So if I wanted to pull out the biggest one was actually the square root of 64 and 5. Or 8 root 5. Now, like I said, the advantage to if I use a factoring tree for this is I'm going to see every set that works. 2 and 160, 2 and 80, 2 and 40, 2 and 20, 2 and 10, 2 and 5. And I can see I have one set of 2's, two sets of 2's, three sets of 2's, which means that one of each of them is going to make it out. And then I have the 5 that's left on the inside. 2 times 2 times 2 is 8 root 5. This frequently helps with the problem of not pulling the biggest perfect square out. But you're still allowed to do it either way. The other thing to be careful of is if it says convert it to a mixed radical in the simplest form, but it already has a coefficient, you still need to account for the coefficient on the outside. It doesn't make sense to multiply that coefficient in and then try and pull it out again. So I'm just going to leave that as a coefficient on the outside when I'm simplifying. If I take the square root of 192, then that's going to give me 2 and 96, 2 and 48, 2 and 24, 2 and 12, 2 and 6, and 2 and 3. I have one set of 2's, two sets of 2's, three sets of 2's, and a 3 by itself, but I also have this 2 that's already on the outside that's going to stay on the outside. So I have a 2 from here, and then I have a 2 from each of these sets. So the 2 that was on the outside, one from each of the 3 sets of 2's in there, and the square root of 3. And when I multiply this back out again, 2 times 2 times 2 times 2 gives me 16 root 3. If I have 3 over 4 and the square root of 160, then that's the square root of 16 times the square root of 10, which means that I have 3 over 4 times 4 times the square root of 10. 3 divided by 4 times 4 is just 3, and the square root of 10. If I'm trying to simplify from a fraction, I look at the numerator and the denominator separately. This is going to be the square root of 7 over the square root of 9, and the square root of 9 is actually just 3. And I've simplified it. I could also express this, if I want to make it a coefficient, as 1/3 and the square root of 7. Either of these would be acceptable.